So thank you. Thank you for your patience as we wait for the clock to turn off on the hour. So our speaker today, Jim Peebles, is the Albert Einstein Professor Emeritus of Science at Princeton University. And that's the last official thing I'm going to be saying today. It is really not possible to do justice to Jim's career in an introduction. So let me not try, let me get out of the way that failure at the beginning. And just, I wanted to say sort of three different things. First of all, Jim has been central to the development of cosmology as we know it from a very early stage, when in collaboration with Dickey, who was his thesis advisor, he predicted the cosmic microwave background radiation. The first of very many, very substantial contributions to cosmology. He also is the author of 3 very beloved and well-read books. And there's no other series of technical books by one author that I own 3 separate volumes of. Physical Cosmology in 1973, I think it was. The Large-Scale Structure of the Universe in 1980 or thereabouts, which actually acknowledges me, strangely. And Principles of Physical Cosmology. Notice the books get fatter with time. And that's not because of the prose becoming more extended. I thought it would actually be worth reading from the introduction to the first of these. This came out in 1971. I purchased it in 73. In cosmology, the reliance on physical simplicity, pure thought, and revealed knowledge is carried well beyond the fringe because we have so little else to go on. By this desperate course, we have arrived at a few simple pictures of what the universe may be like. The great goal now is to become more familiar with the universe, to learn whether any of these pictures may be a reasonable approximation, and if so, how the approximation may be improved. The great excitement in cosmology is that the prospects for doing this seem to be excellent. I think that was a very prescient remark. And with that, I'd just like to observe that Jim has won so many prizes that I actually had to go to Wikipedia to get what is probably an incomplete list. But he's been awarded the Eddington Medal, the Heinemann Prize, the Bruce Medal, the Gold Medal of the Royal Astronomical Society. Do you remember all of these? The Gruber Prize, the Harvey Prize, the Shaw Prize, the Crafoord Prize, and the Dirac Medal. It doesn't get much better than that. With that, I think I'd better just sit down and give the floor to our speaker, Jim Peebles, who is giving the annual Sackler Lecture for 2016. Thank you.
Charles, thanks for those kind remarks. I love that introduction. I don't remember writing it, but it captured the times very much so. So I think that the development of our now well-tested world picture can be traced back to the year 1916, one nice round century, and discussions between Einstein and de Sitter on the nature of the universe as indicated by his theory of general relativity and by some of the philosophy surrounding it. As you recall, Einstein was very taken first with the remark that surely motion is relative to other matter. There's not an absolute significance to it. And surely inertia, similarly, is relative. Inertial is motion, accelerated motion relative to other matter. Now, Einstein at this point knew perfectly well that in his general relativity theory, one can have a universe in which there is an object outside of which space is asymptotically flat, dead empty. This object could rotate in general relativity theory. It would have all the usual effects of rotation, but it would be rotation relative to nothing. Quite contrary, Einstein remarked that if this universe were constructed this way, Mach was wholly wrong in his thought that inertia as well as gravitation depends upon a kind of mutual interaction between bodies. It's dated later, but I think from the context it's very clear he had this in mind in 1916, discussing with de Sitter the notion that perhaps in dead empty space, this is a natural line element. Degenerate, that's the edge of the universe. And that the presence of massive hypothetical bodies out there somewhere caused locally the metric to change to an approximation to Minkowskian. De Sitter, Einstein did not ever, I found no publications by Einstein on this notion. De Sitter, though, did publish and comment in 1916. These hypothetical masses, well, you can read it. De Sitter drew no punches. Einstein certainly agreed, I think, because the following year he introduced the notion that perhaps Mach's ideas, Mach's principle, is embodied in the assumption that the universe is homogeneous, the same everywhere. That certainly, by fiat, gets around the problem of the isolated body that's rotating relative to nothing. There are no isolated bodies. The universe is the same everywhere. In making this assumption, Einstein was being both remarkably bold, which we know he was, and remarkably ignorant. Astronomers then had been counting stars in our galaxy and had established pretty convincingly that our galaxy is an island universe of stars. There was speculation that other spiral nebulae are other galaxies of stars, and it was known full well that these spiral nebulae are distributed in a decidedly clumpy way around the sky. The absence of galaxies near the plane of our Milky Way galaxy was known. Some thought it might be due to obscuration, which is correct, but above and below you see the vast difference in numbers of nebulae. Here is the situation in mid-1960s, early radio source catalogs. In this catalog, you must ignore the hole in the center. You should ignore this hole because this, I don't know whether it's Cassiopeia, I think it might be Cygnus A. Right. In any case, it's a bright radio source nearby that causes the instrument to be confused. Apart from that, what you see is Einstein's vision. Here is an example of the pure thought that I mentioned in that introduction. By pure thought, Einstein arrived at the right picture of the large-scale nature of the universe. You should be impressed by that. You should also bear in mind, of course, that we tend to remember successes more than failures, and so perhaps there's been some bias there, but even so, I'm impressed by the power of pure thought when combined with luck. An example, I say, of the way we do science. So, that's a lesson we should all bear in mind. The expanding universe concept, it was at first theory-driven. One had the assumption of homogeneity based on no evidence. It was Hermann Weyl, I think, who first noticed that if parts of this universe should be expanding, then there would be a linear relation between recession velocity and distance. He didn't have a complete theory, though. That came from Friedman, who had analytic solutions to Einstein's field equations for an expanding universe. But Friedman was unfortunate to have been born a little too soon. He didn't know about the evidence. Lemaitre was born at the right time to combine independently derived line element for a homogeneous universe that requires, if it's expanding, either contraction or expansion, redshift proportional to distance. He recognized that relation and he applied it to data. For that reason, I consider him the pioneer. In fact, in the late 20s, I think he understood relativity theory as applied to cosmology better than anyone, Einstein, De Sitter, all of them. A true genius. And here, just a little clip from his 1927 paper. He is observing that if V equals HR, and if I have a catalog of data in which I'm given for each galaxy a V and an R, then if I take the average of the V's and divide by the average of the R's, I have an unbiased measurement of H, the constant of proportionality. Indeed, he derived it, and he got very close to, using Hubble's data, he got very close to Hubble's coefficient H. This is the reciprocal of H in length units. He was a genius. He was not a very sophisticated person, though. He published this result in a journal that I'm sure has many positive features, but the in-crowd didn't read it. And so his great result was just not noticed. It was only after Hubble claimed detection of the redshift distance relation that his paper was noticed. I like the story of how the empirical evidence for expansion developed. We can go back to our friend Percival Lowell, who was from a rich, socially prominent family here in Boston. Perhaps you all know the verse. So now we are in Boston, the home of the bean and the cod, where the Lowells talk only to Astors and the Astors talk only to God. He was one of those Lowells. He became fascinated with the idea that Mars may be inhabited by a advanced civilization that, to conserve resources, had built vast canals running across the planet. He used his personal fortune to build an observatory to look for this effect. He is honored by astronomers for choosing to build that observatory in a site convenient for astronomy, Flagstaff, Arizona, or thereabouts, rather than convenient for the people who wanted to use it. And second, he hired excellent people to instrument and use the telescope, including particularly Melvin Slipher, who found that spectra of galaxies are shifted largely toward the red. To test the redshift distance relation, he did distances here at the CFA. Henrietta Leavitt got the variable star luminosity relation. Here, Edwin Hubble applied it. In his work, he was magnificently supported by Milt Humason, standing in the background but doing the competent work. Hubble loved ceremonial occasions. You can tell he's very happy here. Einstein, from all I read, hated such events. I'm sure he wanted to be somewhere else. But anyway, here in the lower left is Hubble's relation. I'm not sure you would get all that excited these days, but he was. And his work with Humason took them out by 1936 to a redshift of 0.1, 10% of the velocity of light, in the year when I was 1 year old. Just think of that. It took another 7 decades to get the next order of magnitude in redshift distance relation. Lemaitre, theory-driven, said V equals HR, and it worked. Again, luck with skill and intuition. So discovering the fossil sea of radiation, that linear relation is a good hint that the universe might be expanding, but you need more than that. And luckily, as people all know now, there is a particularly useful fossil from the early universe, the thermal radiation, produced back then and evolving to the present. Here is a thing of beauty, a flowchart of what happened to find it. I should just pause to talk about a few details. 1948, George Gamow had a brilliant insight. George Gamow had the idea that in the early universe, matter may be in the form of the simplest of all atomic atoms, neutrons. Neutrons would decay, neutrons and protons would combine to make deuterium. This is a radiative reaction, so it's relatively slow compared to charge exchange reactions. So once you make deuterium, you can build up heavier elements. He had to resort to the assumption that these baryons were in a sea of thermal radiation in order to prevent this reaction from turning everything into deuterium. In a cold universe, everything clumps together, and that's not a good state for making us. We need a hydrogen. So he said, let us suppose that we are in a sea of thermal radiation. He knew very well the Sahar relation. He knew that if the number densities of these nucleons is small compared to the number density of photons, then there is a very sharp transition at higher temperatures than 10 to the 9th, where photodissociation discourages production of any appreciable amount of deuterons, and at temperatures below this, where photodissociation is strongly suppressed and you accumulate deuterium. So he had a time when structure would start forming. He knew that if you wanted to make it a reasonable but not excessive production of heavier elements, he needs sigma NVT on the order of unity. Cross-section times number density times velocity times time, that's an optical depth. If it's on the order of unity, then you'll have some hydrogen left over and you'll have some heavier elements. He got sigma V from Hans Bethe. He got T from the observation that at 10 to the 9th degrees, the energy density in radiation is enormous compared to the mass density equivalent in matter. And so using the temperature, he has a mass density in radiation that gives him expansion time. So we could solve for n 10 to the 18 per cubic centimeter when the temperature was 10 to the 9th K. Now it's an easy exercise, which he didn't do, to take the temperature at 10 to the 9th, the number density 10 to the 18. You can do this perhaps in your head. Expand to the present number density. He always used 10 to the minus 30, and you get a temperature, 8 degrees. Wow. So close to what's observed. He didn't take this step. Alpha and Herman did, but under the wrong assumption. They assumed that all the elements were made in the hot Big Bang. There, of course, is a mass barrier at 5. You can't, by neutron capture, get beyond helium. And that already, Alpha had pointed out in his thesis, would seem to stop element buildup past helium. But they said, all right, let's suppose you get past that barrier and we produce all of the elements. That gave them a slightly different temperature, 5K. So in this case, I'm inclined to split the rewards. Gamow had the right physics. But it was Alpha and Herman who got the brilliant idea, let's compute what the temperature would be today. And as is notorious, whoops, but now I got to go back. So just the timeline. Coleman, 1934. Fill a universe that's homogeneous and isotropic with radiation, let it expand. The radiation will remain thermal, it'll just cool off. No thermalizing dust required. McKellar, 1941, cyanogen in interstellar space shows excitation to the first excited level of rotation. What's exciting it? Collisions seemed inadequate to do it. The excitation is equivalent to a temperature of around 2.3 K. As we know, that's very close to 2.725. He had it, but no one noticed. I should say, well, let's go with the abundance of helium first off. Gamow had in mind about 50% helium. It's a mystery where he got that, except that he might have been thinking about a Martin Schwarzschild paper for the structure of the sun, which had about that mass fraction in helium from the 50s. That solar model was wrong. He had the convection zone below the radiative transfer zone. But yet somehow the solutions are stable enough that Martin got in the right ballpark for the helium abundance. Fermi and Turkovich completed the Gamow's calculation in more detail. They got about 30% helium. And now I should tell you about this Ann Arbor conference to introduce, well, George Gamow, who spoke at the conference, Don and Irene Osterbrock here, Jeff and Margaret Burbidge here. I think that's Alan Sandage. Would somebody know? I think so. Anyway, Walter Bada, the leader of the conference. Ed Spiegel, who you may know, a young guy then, took this photo by setting up a camera on a tripod. Where? Who did you say?
Owen, point yourself out.
Where are you, Owen?
Next to Gamow.
Is that you? I love it. You published the names of all of these people, but this is a sharper image.
Yes.
All right. Late 1950s, Jeff Burbidge published a paper in which he observed that the abundance of helium in the Milky Way is surprisingly high. He had attended that conference. We don't know whether he listened to Gamow's talk, and we don't know whether, having listened to the talk, he took Gamow seriously. But in any case, Burbidge said this result is surprising and left it at that. Didn't talk about the notion of a hot Big Bang. A few years later, Osterbrock and Rogerson got Y of around 0.32 and pointed out that this high abundance is understood without difficulty on the explosive formation picture from a review article by Gamow the year after he made that great theory. There was the first published suggestion of a fossil from the early universe. A Nobel Prize within his grasp, but no one noticed. until 1964, just as the microwave background was discovered by Hoyle and Taylor, who did recognize that the abundance of helium is a problem if you assume it's made in stars, but easy to understand in a hot Big Bang. Meanwhile, Dickey, during World War II, was here at MIT, Radiation Laboratory, inventing radar devices and also a radiometer, a device capable of measuring the flux of thermal radiation at temperatures down low. This was a byproduct of a study of opacity of the atmosphere at centimeter wavelengths for purposes of going radar at shorter wavelengths for better angular resolution. Water vapor was the real culprit, so he went to a place where it's very humid, Florida. He made the measurements of opacity of the atmosphere, and he also, as a byproduct, put a bound on the radiation coming from outer space, equivalent to about 20 K. You could wonder what would happen if he had taken his apparatus back here, put it on top of that MIT temporary building in the dead of winter, and repeated the measurement. How close would he have got? In any case, 1959, Bell Telephone Laboratories, experiments in microwave transmission for communications, the forerunner of those horrible cell phones that we see all our students wandering around with, had a dirty little problem, excess noise of a few degrees that they couldn't account for. It was a little secret in the Bell Telephone Laboratories for the next 4 years until Penzias and Wilson in 1964 applied Dickey's technique of switching to demonstrate that the noise was not coming from the instrument. Was it coming from outside the instrument? Well, they tried all sorts of tests. It is greatly to the credit of Penzias and Wilson that they could not find any source for this radiation, and they kept complaining about it until someone finally heard them. In particular, Bob Dickey had suggested, quite independently of all these other considerations, that a hot universe is somewhat attractive. Why don't you young guys in my group build a radiometer, a Dickey radiometer, look for this radiation? He said to me casually, and why don't you go look into the theoretical implications of finding this or not? And, you know, that set my career. Anything more to say here? Well, Bell and Princeton meet. Oh, here, this is a 1959 publication. Here, to those, I'm told, who know about this stuff, that's very suspicious. This horn reflector antenna was designed to be very strongly reject back lobes coming in. Perhaps if you're of a certain age, you'll have noticed when we communicated with these things transcontinental, and on telephone poles, you'd see them pointing in opposite directions. One receiving the microwaves, the other transmitting them forward after amplification. And these things back to back had to be very insensitive to back lobes or you'd have horrible feedback. This then was cooking the books to make the sums come out even. Here's Bob Dickey, Annie, their firstborn Nancy, 1945. The war has ended. He's going to move soon to Princeton. Here are Penzias and Wilson. Here, well, that's Dave Wilkinson and me. And you wear too. And what happened next from the late 1960s through to 1990? It's a long time. We were obsessed by evidence of small departures from a perfectly thermal spectrum. If these anomalies had been real, it would have been interpreted as energy released by energetic events in the early universe. Some sort of explosions had to provide a lot of energy to make that excess. Those explosions would have certainly changed the angular distribution of the radiation. And so in measuring the anisotropy of the radiation, the fluctuations in intensity across the sky, you would be studying the signatures of those horrible events in the early universe rather than early universe physics. The situation changed so abruptly in 1990. Here is an up-to-date version of the data as obtained later. This curve, solid, is not theory. That's the observations, with errors small compared to the width of the line. Truly spectacular. Here are then discrete measurements at frequencies. Maybe you can see the dotted line. This figure belongs in my selection of iconic images of illustrations of the way the universe is. So simple, of course not by any means simple to make, but so simple and yet the implications so deep. The universe as it is now is optically thin at these wavelengths. Therefore, it can't have forced radiation to relax to statistical equilibrium. To have released statistical equilibrium, the universe had to have been a very different state at one point or another, dense enough to be optically thick, to force relaxation to this thermal spectrum. It's very deep. This simple image is telling us that our universe is not forever, it's evolving. That's a wonderful thing. I have taken a vow never to show this image without showing the fact that there were two groups. Here, Dave Wilkinson again, John Mather, Nobel Prize for this miraculous, wonderful work. Admiration for him as a postdoc with a very thin publication record. He took 15 years off his life to be PI in this experiment. He sits there at the launch pad watching his 15 years sitting on top of a bomb, watching them light the fuse, and if it explodes on launch, where is he? He has the respect of close colleagues, but he has a very thin publication record. I don't know that. I could not stand that. It's not well advertised, and this is why I've taken the vow, that there was a second group, University of British Columbia in Western Canada, Herb Gush, looking very professional in that white jacket. Here are his two colleagues, Ed Wishnow, Mark Halperin, and this is one of my favorite of all time pictures of scientists at work. If you didn't know that these people had done something truly great, if all you had to judge them by was this image, would it inspire confidence? Okay, so good. On we go. My next, even more miraculously condensed diagram, we have the notion of dark matter, which originated in about 1980, plus or minus 2 years, through the convergence of a remarkably broad number of developments that seem all to have come to a head just at the right time to give us this theory. I'll be looking for comments on whether I'm exaggerating, but let's notice first the astronomer's dark matter. I date the acceptance of dark matter by the astronomical community to 1979 because of the paper by Sandy Faber and Jay Gallagher, Something's Happening at the White House, It's Cold Out in Wisconsin. And in a lengthy set of discussions of evidence for dark matter that is largely draped around the galaxies, they gave this annual review, and I love this concluding remarks. After reviewing all the evidence, it is our opinion that the case for invisible mass in the universe is very strong, and we think it likely that the discovery of invisible mass will endure as one of the major conclusions of modern astronomy. Quite right, of course, but this is not the sort of word you would use if you were addressing a community who were already convinced that dark matter is real. Although the evidence for dark matter goes back to the 30s with the problem of high velocity dispersions in clusters, it took the community a long time to accept it. And it accepted it at a very convenient time, just as we needed non-baryonic dark matter. So, why am I doing that? I wanted to go this way. So, that was a key driver to the introduction of cold dark matter. Another key driver was that we had improved measurements of the anisotropy of the microwave background radiation. The fluctuations across the sky less than a part in 10 to the fourth. In fact, to begin with, both groups had thought they might have seen something, but I think already in 1981, David Wilkinson was telling me in private that that was going to be turned into a bound. And indeed, a very important bound. The radiation is strikingly smoothly distributed. Meanwhile, we have the fluctuations in the distribution of matter. And if galaxies are at all good traces of mass, then the mass distribution is highly clumpy. If gravitational growth produced the clumpy distribution of matter, then it became very difficult to understand how the radiations could have remained so smooth. It approached the nature of a crisis. The crisis, of course, was resolved by the postulate of dark matter, because you recall, in the early universe, radiation and baryons are coupled as a plasma with a very high pressure due to the radiation bound to the plasma by Thomson scattering. That high pressure of the plasma radiation fluid means nothing much can happen in the way of structure formation until decoupling at a redshift of 1,000, and from 1,000 to the present is not enough time to grow that structure in the matter distribution, a real crisis. But of course you can reconcile it if you assume non-baryonic dark matter. That line of thought originated in the early 70s, actually, with the discussions that maybe the dark matter, which some astronomers agreed is there, is in the form of massive neutrinos with masses around 10 volts. That is not acceptable as a theory of galaxy formation, because neutrinos that light would move quickly and smooth out small-scale structure to the point that structure would have to form top-down. Where is top-down? Well, I guess I left it out. Oh, yeah, there it is. This is not a viable model. But Lee and Weinberg, 1977, did know about these ideas and did propose, well, let's consider the notion that there is a massive neutrino, a new family with a much larger mass than 20 volts or 10 volts. And they pointed out that if this new family of neutrinos has a standard V minus A interaction, then in the very early universe there will be neutrino-antineutrino pairs. They will annihilate as the temperature drops below the mass, but there will be remnants left over. And if the mass is around 2 GeV, there will be enough neutrinos not to, as they wrote, not to have overproduced the mean mass density of the universe, which they had derived from the old acceleration parameter. We needn't get into those details. No evidence that they knew about the top-down versus bottom-up consideration, but they did give us massive neutrinos that would not resist clustering on the scales of galaxies and up to clusters, and allowing bottom-up structure formation. Those were the elements that fed into the dark matter picture, along, of course, with the initial conditions. Interesting situation there. In those days, we said, before inflation, we said, well, scale invariance, that's only natural. Because if it's not scale invariant, then curvature fluctuations will dominate either at small scale or the large scale end. Gaussianity, well, that's the simplest of all possibilities. Let's work with it. And let it be adiabatic. Well, of course, we also discussed isocurvature, but it was on the books as an interesting possibility. The important role of inflation was that it led an air of credibility to those set of initial conditions, because simple models for inflation produced them. That was certainly important. As a side remark, of course, we noticed that inflation convinced people that there shouldn't be any space curvature. And if there's no space curvature, then why don't we drop that dumb lambda too? Because an observationally interesting value of lambda corresponds to an energy of a millielectron volt. And that's really not a manly energy for high energy physics. So the world became convinced of Einstein de Sitter. And indeed, Bob Dickey and I may have introduced the concept that if the universe is not Einstein de Sitter, which is to say zero space curvature, zero cosmological constant, then because we know the matter density is omega fractional contribution to expansion rate is not far from unity, and since the relative contributions of matter, curvature, and lambda change differently as the universe expands, we live in a golden era just as the universe started departing from matter-dominated expansion. A coincidence that seems absurd, so let's remove the coincidence by making omega matter equal to unity. Another argument for pure thought and elegance, and it failed miserably. Shall I say anything more here? No. Well, hey, we should notice, this was a time of great intellectual ferment. Tom Kibble. Well, let's suppose structure formation formed out of cosmic strings. Jerry Ostreicher. Maybe explosions caused structure formation. They didn't go anywhere, but they illustrate the ferment of the time. Lots of ideas bubbling up. As I look back on those times, I didn't notice anything special happening. It was just going along day to day. It's only now I stand back and look at the history of this subject does it occur to me, wow, the early 1980s, 1980 plus or minus one or two, was a special time when a lot of things came together. One can see that there were reasons for things to come together. In particular, technology was improving dramatically. It was driving the ability to measure anisotropies in the microwave background, and it was driving measures of methods of measuring relative motions of galaxies, rotation curves and the like. So it's perhaps not totally surprising that significant bounds on anisotropy and significant measures of mass distribution came together at about the same time. I would love authoritative figures to tell me whether or not there are other interactions that caused this conversion, or was it much of it strictly, purely accidental? Things just came together. They deserve great credit for this because they were courageous. I remember Jeff Burbidge. You guys are just riding the bandwagon. They weren't. They were taking data seriously. Another convergence of results, it's two results, but converging at remarkably similar times from very different directions, coming to the same conclusion, we need lambda. Alan Sandage, his great dream, lets you measure the redshift magnitude relation for galaxies. Beatrice Tinsley, Alan, you can't do it. You'll be measuring the evolution of galaxies. Then the supernova people, here they are, Saul Perlmutter, Adam Rees, Brian Schmidt. I love this photograph too. I've taken to liking photographs. These guys, I've never seen these guys so neat. And here are three more winners of other disciplines. The founder of this prize, Sir Run Run Shaw, made his fortune in entertainment, movies, kung fu movies, among others. He is famous in China for his support for education. He is with the then Chief Executive Officer of Hong Kong, but I draw your attention to his suit. That was bespoke. So where are we? Oh, here it is, an early version, 1999, showing that accelerated expansion of the universe. At this point, it is very important to pause and reflect on how the reaction would be if this were the only piece of evidence for Einstein's cosmological constant for accelerated expansion. We may predict the community would fall into three camps. One camp would say, this curve you've traced is the steady state prediction, which is true. Shouldn't you therefore buy steady state? Well, of course, the answer is no. We have the microwave background. How are you going to produce that in the steady state there? But some would argue that way. A larger group would say, well, all right, we've got to learn to live with lambda. But I bet the largest group would say, look, you guys who've made these measurements, I know you've done a superb job tracking down every possible cause of evolution of properties of supernovae. But which am I to believe? That this stupid lambda exists, or that you've omitted one very subtle correction to evolution of these supernovae? So important that at that very time, the CMB anisotropy spectrum was starting to be traced out. Perhaps here you can see shaded areas. That was the result of measurements before 1999, as compiled by Lyman Page. And the measurements reported in that 1 year, 1999, showing beautifully well that spike. The curve is the now standard theory and prediction and verification. The position of that peak, if you believed in the CDM type scenario, but with lambda, tells you about lambda and gives you the following situation. The year 2000, within relativistic theories, and you know we should pause to reflect, the general relativity was not well tested in those days, and the best tests on the scale of the solar system are on scales, say, 10 to the 13 centimeters. General relativity is being applied on the scale of the Hubble length, 10 to the 27 centimeters. It's some 14 or 15 orders of magnitude extrapolation. Would you trust a 14 or 15 order of magnitude extrapolation? Yet people did it without much thought. Turned out they were right, but so here is a constraint on two parameters, omega matter and omega lambda. You need two parameters because the three sum to unity. Here is the line of zero space curvature. Here is a constraint from the supernovae. Here is the constraint from CMB anisotropy if you accept lambda CDM or CDM. Not shown here, so I take the liberty of showing a later example of the same plot, but here Ned Wright has given a color code to indicate the cosmological constant you need as a function of position along this line of degeneracy. And you notice in here we're making a transition to around yellow, the measured value. So you see here something truly magic. Three lines of observation are coming together. Observations done on very different techniques, on very different phenomena, but yet converging on a number around here with the right local distance scale, the right redshift magnitude relation, and the right CMB anisotropy. That is what made me a believer. Just marvelous to see these evidence coming from three directions into concordance. Well, I have another topic to deal with, so I'm going to end here this part of my lecture just by reminding you that the story doesn't end there. Exquisite measurements that test the cosmological models in all sorts of different ways. There's a song, I've looked at love from both sides now. Yeah. Joni Mitchell, a Canadian. She sang at the University of Manitoba, but alas, the year after I left for Princeton. Anyway, we've looked at the universe from all sides now, and it's consistent. It's just wonderful. So I mean, I have to conclude that the dark matter notion with lambda is about as well supported as it gets in natural science. A remark on this part of the story, which I take from Mort Roberts, who was one of the pioneers in getting rotation curves of galaxies to show that they're have draped around them dark matter. What took us so long to accept dark matter? How does it differ from the instant acceptance of the extragalactic nature of the nebulae when Hubble announced Cepheid detections? We can say a very similar question here. Why is the community so reluctant to accept lambda, yet so willing to accept CDM? I have in mind here at the time 1980, plus or minus 2. In 1979, the community was very reluctant to even accept the notion of non-baryonic, of dark matter. In 1980 plus 2, the community was in love with CDM, with its hypothetical dark matter. Such a change. Why? Well, it's just the tides of fashion. Why did the community take so long to notice that the abundance of helium is cosmologically significant? Or maybe. Why did no one in the community think to look for Gamow radiation before it was found? Many years after the Gamow paper. Why was the community so little concerned about that spectacular extrapolation of general relativity? And that leads me to the final question. Are we so smart now that we won't make such mistakes? And I offer the answer. Thank you. No. So, wait. When did I start? And it's only 4:44. I'm allowed another 15 minutes. I want to offer some thoughts on what we may be overlooking. So, Tracy McGaw, a brave person, pushing the theory of, Mond, but he has data. And here he has plotted on the look at disk galaxies, see the motions of the stars at different distances from the center. Knowing the motion of stars at a given distance from the center, take v squared over r, that gives you an acceleration g obs, which is plotted vertically. Here is the standard expression for the acceleration you expect if the mass is traced by the baryons. That's g bar, plotted horizontally. Here, each line is a separate galaxy. Here is the mean trend. But notice now, up here, do you recall the old conspiracy? The rotation curves of flat galaxies do something really curious. In the center, that rotation curve is supported by the mass in baryons. In the outskirts, it's supported by the mass in dark matter, and the curve is flat, running from one to the other. A conspiracy, here illustrated by the way these curves peel off from the diagonal line, which is acceleration supported by baryons, to the slash line, nominally acceleration supported by dark matter. This is a beautiful illustration of that darned conspiracy. Why did lambda CDM conspire that way? I have no answers. Here, the fundamental plane for elliptical galaxies. The elliptical galaxies have a wonderful relation between their radius, their velocity dispersion, and their surface brightness. Here, where is his name? Collis, Matthew Collis, and his group have plotted each symbol is an early type galaxy. The green ones are singletons, more or less isolated ellipticals. This cross, I wish he had chosen a better color scheme, groups and clusters. The point, which has been demonstrated in quite a few different surveys now, the structure of an elliptical doesn't care where it is. To remarkably tight constraints, an elliptical acts like an island universe. We hear a lot of talk about the growth of ellipticals, but yet the end product doesn't care about how it was fed. Isn't that remarkable? Here is, well, this takes a few words to explain. This is Sloan data. Measure the mean spectra of a lot of ellipticals. Divide the ellipticals into two classes, those with low velocity dispersion and those with high velocity dispersion. You can read the numbers. Take the ratio. The ratio drops with increasing wavelength. That's because the massive ellipticals are in the denominator, and everyone knows that a massive elliptical is redder than a lower mass elliptical. This trend downward is just that effect. But the data have been further subdivided into those in low density environments and those in high density environments, red and blue. You see some distinct differences. Look at this spike. I gather that's H alpha, and it appears in the field. Field ellipticals gather in H hydrogen from, there's more of it around them, so they have a stronger line. You see other differences along in here, but to my way of thinking, what is so dazzlingly fascinating is how similar the spectra are of low mass and high mass ellipticals. An elliptical knows how bright it is. It displays a color. But an elliptical doesn't care where it is. Tully-Fisher relation. A relation between luminosity and circular velocity in disk-type galaxies. In this survey, the lowest quartile, middle, highest quartile. The solid line common to each. And again, the Tully-Fisher relation between luminosity and circular velocity. Well, the circular velocity surely knows about the mass. I should have said line width, baryonic mass. You tell me the baryonic mass, I'll give you a pretty good estimate of the circular velocity, or conversely. They're correlated and they have a definite relation, but they don't care where they are. Isn't that a remarkable regularity? And here, just why do galaxies care so little about their environment? I am, of course, excluding rich clusters where there's a clear environmental effect. The gas swept out of them. But in the field, it looks as though galaxies grew as island universes. Galaxies grew as island universes. Despite what all lambda CDM simulations tell you, galaxies grow by mergers. Here, well, I'm getting into the arcane, but, well, this is good fun, isn't it? So here are the 277 ISIT galaxies with known distances within a radius of 8 megaparsecs. The distances from Brent Tully and his group. The red ones are those more luminous than 10 to the 10th solar luminosities. The black ones, the many, many dwarfs. Notice this area, almost a third of the volume, is empty, aside from one lonely little galaxy. I show only one example. Here is a negative, and there is the little clump of stars. You can see perhaps the contours of H1. It's surrounded by a vast H1 envelope. Out there, floating so lonely. So lonely. Why so few galaxies in all this space? What else should we look at? Oh, the big galaxies like to be in the plane of the local supercluster, as do the little ones, but they don't care. NGC 6946 is here. It looks a lot like M101. It's up here, or like M94, which is on the plane, or like NGC 253, that very flat galaxy, which is also in the plane. Marvelous. Marvelous. The big guys and the little guys are very similarly distributed. That's not what you would expect in a naive model for structure formation in the lambda CDM model. One would say that in this region, the overall density is low, and so those local density fluctuations that would have made an L-star galaxy instead make a dwarf galaxy. But this expected segregation of L-star galaxies from dwarfs is just not observed locally. I will come back to this concentration of the plane after I remark. You know, we're running out of time, and that takes too much talk. I love this one. So here we see that the galaxies nearby love to sit on a plane, the little plane of the local supercluster. Here is a plot of the distribution of galaxies in a sphere 10 times the radius of that 8 megaparsec sphere. This is 80 megaparsecs. These plots require a bit of explanation. Imagine that this disk, which is a plane, is tilted so that it's along the line of sight. For each galaxy, plot out where it is and run. This is the normal to the disk. You must imagine that the disk has been straightened out. This is the position of the galaxy. Here it is projected onto the plane. So the length of this line is the distance above or below the plane. The position on this ellipse is the position within the disk. So that's pretty clear. And these are the rich clusters, 9 rich clusters within this region. These are the 30 most luminous galaxies at 60 microns. Do you see? These guys like to be in the plane defined by all the galaxies in a sphere this small, whereas these guys could care less about that plane. What is going on? Are you as shocked as I by this? Well, perhaps not, but I'm easily shocked, let's face it. So I ask, is something of value to be learned from all of these things? The scarcity of galaxies in the local void, the similar appearance of L-star galaxies in the outskirts of the local void and in the crowded local plane, similar space distributions and relative abundances of nearby dwarfs and L-star galaxies. This last thing, the preference of clusters at 80 megaparsecs for the plane defined by galaxies at 10 megaparsecs, whereas luminous galaxies could care less, the Gauss effect. The evolution of field galaxies as island universes. I haven't mentioned the disk phenomenon, but it's there. And what strikes me about this list is that we have so much talk about dwarfs too big to fail and about cusp phenomena. They are challenges for lambda CDM, but I have somehow the feeling that they're a selection among a broader class of challenges. Why do people so much discuss these two challenges and not the others. I submit that it looks to me like a herd effect. And that also that we are required, each of these can be accounted for by suitable postulates about how things operated. But I put it to you also that we're having to make a lot of special hypotheses. We are having to apologize for lambda CDM a suspicious number of times. And I'm wondering if that's because we're no longer smarter than we were in 1980, and that we are missing something really interesting about the large-scale nature of our universe. So let me just conclude by the statement I really love. I've talked a lot about advances by pure thought, but in the end, those advances became real because people looked. You can see a lot by just looking, and I offer here examples of people just looking. Thank you.
Thank you. I think I didn't comment adequately at the beginning that this is the Raymond and Beverly Sackler lecture. It's an important part of our calendar, and I should acknowledge our benefactor. Let me take the first question, if I may. You, in your history of the 50s and 60s, made no mention, I think, of steady state theory, which did roil matters a little bit back then.
Yes.
Did you just think it was a mistake to have gone down that path altogether, or?
I think steady state theory did a great service to the subject by infuriating observers who set out to disprove it. Certainly in radio astronomy, that was the goal by Henry Brown. No, not Henry Brown. Ryle. I must admit that when I first learned of the steady state theory, I was shocked. I said to myself, they just made that up. I didn't pause to think that the hot Big Bang theory, or in those days the Big Bang theory, was also just made up. So no, I think it was, and one sees wonderful parallels to inflation in the steady state theory, both just made up, both having very similar physics, de Sitter space-time, and maybe, who knows, about inflation. But no, steady state theory was important in goading people to do new research. It, of course, died with the CMB thermal spectrum.
So, other questions?
Jim, how do you explain the fact, the sociological fact, that there is this inversion of attitude where the younger people are more conservative than the older people?
I'm not going there. Michelle.
In your history of dark matter, you're going back to Gallagher and Faber. Why not Vera Rubin? Because after all, she was the flat rotation curve, so what was out there?
Oh, well, here she is.
Right in the middle.
Why didn't I mention her?
Yeah.
Well, along with Mark Roberts and a few others, they all made important. Yes, in fact, Vera and Ford had this image intensifier tube, very high tech for the time, in which one saw the wavelength of the line across the galaxy. It was a step function in many cases. On one side of the galaxy, blue shifted, on the other side, red shifted, as a step function. That was such a dramatic visual demonstration that it grabbed me and many, I'm sure. It was important, but still, the radio astronomers were very important too. And, well, I think it's a fact that although they were doing important work in the 1970s, they weren't persuading the community of astronomy until, I think, Faber and Gallagher. Those who lived through those times may have different recollections, but it was my feeling that before Faber and Gallagher, I was thinking of dark matter, of course, but I was a fringe person. I don't think I was following the established thought until Faber Gallagher. And you know, Faber is not a person to suffer fools lightly. So she had the influence, as well as Jay did.
Anybody else? Yes. Where's that?
In terms of particle physics, there's still a lot of work. People are trying to understand what other particle science is, what their implications if we find them, what they would do for cosmology. Is this something that you find interesting or important?
Oh, absolutely. Show me a dark matter detection. It will be, my hope is I will be surprised. And I think the odds are good. Because, well, the obvious things have been done in dark matter detection. You're scraping the bottom of the barrel. Of course, one of the great problems in dark matter detection is these are multi-year experiments. You don't easily change direction. So in the vast parameter space of candidates, there have been channels drilled. But it's hard to explore all of parameter space. And that will be done, I hope, by small groups thinking independently, taking off in some new direction. And as I say, my hope is, and expectation, it'll be something surprising.
Kathy?
Yeah, I mean, I like your final slides pointing out all these problems, issues. Do you have any speculation to offer? Could that tell us something about the structure of dark matter or the properties of dark matter?
I have the same question you have. What is it trying to tell us? My thoughts on that subject are just too ill-formed for me to mention. I leave that for the younger generation. You are not running out of things to do in science.
Erwin.
Just an historical question. Why do you think that Zwicky, who is a pretty good guy, his apparent discovery of dark matter was ignored? As far as I can tell, no one picked it up.
You knew Zwicky?
I saw him the evening before he died.
He was not the most pleasant person in the world. He had his little ways. I saw him talking to some of the junior people. It was not good. He, though, was a genius for his time. He had just the right instincts, ability, whatever, to do fundamental work in many fields, from supernovae to dark matter to... I spent several years of my life analyzing his catalog of galaxies, the one that you guys used as finding charts for a much better catalog of galaxies. He was great, but such a person.
Do you think his personality was the reason his result was ignored?
Yes. What do you say?
Well, it was kind of actively rejected. I actually worked as his observing assistant for a couple of months, and he was extremely irascible.
Yes.
And very much given to telling everyone how he had done everything
Yes.
faster and smarter and better and earlier than they had.
Yes.
And so people knew about it, but they were inclined to reject it if they could. So.
You remember the statement that in reaction to someone's claim, it's trivial, no, it's wrong, it's trivial, and I did it first. I think there is that personal element in what we all do in science. Enough of this objective science business. Would you disagree?
Okay, we'll take one more
I
question.
would hold Judge.
Would you care to speculate what the implications of gravitational astronomy will be on cosmology?
On cosmology. Yes. No. It's clear, a new field of astronomy opening up. How could you not be excited? You're going to, again, you'll be surprised. After all, it's surprising to think that there are a pair of, 30 solar mass black holes close together. Do we know of any other sort of 30 solar mass black hole detected? They're all smaller or much bigger. So astronomy is going to be given a real boost. Cosmology Well, you know, there's a deep question. How did these galaxies get central massive black holes? Again, it's not something that you would naturally expect in lambda CDM. That's not to say lambda CDM is disqualified, therefore, but rather it's another apology we have to make for this theory. But what is the real, why are these masses so big? How did they grow in concert? And you know, it is worth noticing that there is a pretty impressive correlation between central massive black hole mass and bulge luminosity, except that there are many bulge-free spirals that have central massive black holes. It's a complicated problem. Coevolution has got to be very complicated. And what does this say to cosmology? Well, did those early seeds for the massive black holes originate at very high redshift as some sort of primeval object? Or is there something happening? Is there a surprise to be drawn from the existence of these massive black holes, particularly at redshift 8, where you see quasars, which, if we have about the right story, contain massive black holes that formed remarkably early? Wow.
Let's thank Jim again.